So Hardy-Weinberg there's a couple equations here, and it's basically a way of determining, you can determine a couple things. You can determine the allele frequency in a population if you have certain information, and you can also determine the genotypic frequencies of a population. And so we have a couple of equations here. P plus Q equals 1. Now you'll notice that I wrote the P as a capital and a Q as a lowercase, and so I did that for a reason. Does anybody know why? Because P is the dominant allele. So P plus Q represents the dominant and recessive allele frequency in a population. The 1 is, you could also refer to it as 100%. Okay? So 100%, you've got a number of alleles in a population. The 1 is basically talking about that's 100% of all the alleles. Okay? So you have recessive alleles, you have dominant alleles, and that will equal 100% of your alleles. So it's a way of looking at how the allele frequency, and like, let's say you looked at a population's allele frequency for a certain trait. Well, you could come back 10 years later and also calculate it again, and then you could determine if there's changes taking place. If there's changes taking place in the allele frequency, what's happened? What? Evolution. So the population has evolved. If it's changed, the allele frequency, then the population has evolved. Remember what we said? Evolution is the change in allele frequency in a population over time. So if the allele frequency changes, the population has evolved. Okay? And we're only looking at like one individual trait at a time with this. Okay? So P plus Q equals 1 or 100%. So the dominant allele plus the number of recessive alleles equals 100%. Now the second equation you need to know is P squared plus 2PQ plus Q squared equals 1. Now the 1, again, it's 100%. This equation is referencing the different genotypes. Okay? So P squared is our homozygous dominant. So like if you have, two of those dominant alleles, okay? Plus, you have the homozygous recessive, which is 2PQ. So you could probably write it, or you should probably write it like 2 times P times Q. So you're going to multiply those together, okay? And then the last part here, Q squared, and I write it lowercase because this is represents what? Recessive trait. So it's like little whatever, okay? So this is homozygous recessive. So these are all your genotypic frequencies, and they should add up to 100%. Okay? So I can tell you just one thing, and you should be able to figure out all of the other things out of these 5 variables. Okay? So we're going to go through and we'll do a sample here. When we talked about Mendel's pea plants, we talked about pea plants, and a lot of them are characteristically were tall or short. So let's say that Tay is out in a field where Mendel used to work, and it had been abandoned, but there were still some peas growing each year. And she saw that and she went through and counted the peas. So in that pea field, she counted them, and there are 40% of the peas are short. So what I want you guys to do is I want you to use these 2 Hardy-Weinberg equations to determine the allele frequencies and all the genotypic frequencies for those peas in that field. Okay? Good. All right. So after you thought about that for a few minutes, let's see how you're progressing. So we know that 40% of our peas are short. And if you remember back from the genetics unit, short is the recessive trait and tall is the dominant trait. Okay? So I usually like to go through and label out these 5 things and make sure I know what I'm talking about. So big T is tall, little t is short, allele, these are the alleles. Okay? And then I guess we can say percent of the alleles. And then over here, these are your different genotypes. So these 2 up top would be what? The P squared and the 2PQ represent our tall pea plants. Okay? And then little t represents short pea plants. Okay? Because remember, these three things are our genotypes. Okay? And then these two up here are our allele frequencies. Okay? Now, anytime you get one of these Hardy-Weinberg problems, the first thing you want to do is think about, just like most math problems, what have I been given? So out of these 5 variables, which one do we know for sure? We know the last one, right? We know little t. We know how many short plants there are. And the number is what, Katie?
0.4.
So 0.4. So we're going to do the decimal form of the percentage here. So 40% or 0.4. Okay? Now, once you have q squared, does that make sense, Walker? Okay, once you have q squared, because we don't know, you can't look at a bunch of pea plants out in the field, Tay, and know how many short alleles or dominant alleles there are, right? But you can look and see, is it short or is it tall? And so once you know one of those things, like it's short, then we can find this. Now, what do you think the next thing we need to locate is, or figure out? What? Q. So if we've got q squared, we can find q, and how do we do that?
Square root.
Take the square root. So if q squared is 0.4, then q, you would take the square root of 0.4, and you get? Who's got a calculator? 0.6. Do it like an extra decimal. 0.6.
632.
0.632. I would make a habit of running these decimals out a little bit further than usual, just because if you round off on like this first one, when you go to the next one, it's going to round off, and then when you get down here to like 2pq, you're going to be rounded off, and you could be a couple of like hundredths off by that point. So the further out you go, the better off you'll probably be in the end when you do your final answer. And it's really prevalent when you are figuring out like the frequency of albinism in a population where it's like 1 in 20,000 and you've got like 5 zeros. So you want to be mindful not to round off too much, okay? So once we have Q, what's the next thing we can figure out?
P.
What?
We figure out P.
P. So if P plus Q equals 1, then P is going to equal 1 minus Q, right? And so this one should be 0.3, what is that, 68? That's not right. Yeah, that's right. All right, so any questions so far? So a good way to check this, add these two together, they should be 1, okay? And when you get to, what's the next one we can do, Matthew? Are you awake? Sarah, what's the next one we can do?
P squared.
Well, really, either one, right? We've got the information. We've got p squared. We've got p up here, so then naturally we probably do it. So all you do, if p is 0.368, then p squared would be, you do what? Square it. And what do you get?
0.135.
Yell it, Tay.
0.135.
0.135. And then to get 2pq, all you do is multiply 2 times p times q, and you should get, you might got that? Katie, what are you doing? Get your life together.
There's another one.
Should be
0.46 what?
5.
0.465. Does that sound right? 8, 9, yeah, okay. So, this adds up to 100%. We should be good to go. Now, what can all this tell you? Well, let me ask you some questions. What is in the peas in the field that Tay was surveying? What is the percentage of short alleles within all those pea plants? Keep in mind, you can't see the alleles. Okay, you don't know how many recessive alleles are there in place. So, but we know how many recessive alleles are by calculating this. So Mason, what's the percentage of short alleles?
I mean, 63.
63%. So out of all of those pea plants and that trait for height, the percentage of short alleles is 63%, just like the percentage of dominant alleles is 37%. And then Now, it would have been pretty easy early on for Tay to tell us, well, 40% are short. Well, that tells us 60% are tall, right? But there's no way that we would have known how many are heterozygous or homozygous. So if you were asked, like, how many are homozygous tall, it would be 14%. So if 40% are short, 60% are tall, of those 60%, only 14 of those are homozygous tall. Does that make sense? So using these equations, you can figure out a lot of stuff about the different genotypes and the different allele frequencies. You might got questions? Yeah.